What if the most dangerous thing the sun can do to us is not to grow more violent, but simply to turn and face us? 5 days ago, a sunspot larger than the Earth fired the strongest flare of this entire solar cycle, and we got lucky because it was aimed the wrong way. Since then, it has only rotated slowly day by day, until this morning it sits almost dead center on the sun, staring straight down the 93 million mile corridor to Earth. And it marked its arrival with another powerful flare and a blackout that swept the daylight side of the planet. Right now, every instrument here on Earth reads calm. That calm is exactly what the beginning of something far bigger would feel like. If that unsettles you the way it should, subscribe to the Skylab and hit the like button, because we are following this one as it develops. Tell me in the comments where you're watching from tonight, and whether your sky has ever lit up with the aurora. This week, it just might. Now, let's get into it. Part 1. The blackout that already happened. At 2 minutes past 10 o'clock this morning Universal Time, a pilot somewhere over the daylight side of the planet reached for a radio and found static where a voice should have been. A ship's operator watched a high-frequency channel dissolve into a wash of noise. A shortwave listener lost a signal mid-sentence. None of them could see the cause, because the cause was 93 million miles away, and it had already happened 8 minutes before any of them noticed. That is not a figure of speech. Light takes about 8 minutes and 20 seconds to cross the distance from the sun to the Earth, which means that by the time the effect reached the radios, the event that caused it was already old news on the sun. We were reacting to a message that had been in transit since before anyone knew to listen for it. What reached them was the leading edge of a solar flare. The official designation is an M6.9, and if that string of characters means nothing to you yet, hold on to it, because by the end of this it is going to mean a great deal. For now, all you need to carry forward is that this was a serious flare near the top of its class, and that it came from a single scarred region on the face of the sun that has been building toward exactly this for the better part of a week. The immediate effect had a name as well. Forecasters classified it as an R2 radio blackout, moderate on a scale that runs from 1 to 5. To understand what that actually means, you have to picture the top of our atmosphere, a layer called the ionosphere, 100 kilometers and more above your head, where the air is so thin and so bombarded by sunlight that its atoms are stripped of electrons and left electrically charged. That charged layer is what makes long-distance radio possible in the first place. High-frequency signals do not travel in straight lines to the horizon and stop. They bounce, skipping off the underside of the ionosphere and back down to the ground, over and over, which is how a voice can travel across an ocean on a band of radio no wider than a whisper. When a flare's X-rays arrive, they slam into the lowest part of that layer and flood it with extra charge, and instead of reflecting the radio waves, that thickened layer absorbs them. The signal goes in and does not come back out. For a few minutes around the peak of this morning's flare, across the entire half of the Earth that was in daylight, that is what happened. The mirror in the sky turned into a sponge. Think about who lives on that band. Transoceanic aircraft out over the middle of the Atlantic or the Pacific, far beyond the reach of any ground tower, stay in contact with controllers using high-frequency radio, and when it fails they fall back on procedures and, increasingly, on satellite links. But the disruption is real, and it is logged. Ships lean on the same band. Emergency services in a remote country depend on it. Amateur radio operators, the people who often notice these events before any bulletin is issued, watch their signals simply evaporate. It did not go dark everywhere on Earth, and it did not stay dark for long, and no airliner fell out of the sky over it. But for those few minutes, across a hemisphere, the sky stopped carrying voices. That is what an R2 looks like from the ground. Not a catastrophe, a warning shot you can hear. Now here is the first thing genuinely worth sitting with. The flare that did this is not, by the measure that matters most, the biggest thing this same region has produced. It is not even the biggest thing it has produced this month, and yet forecasters spent this morning watching it far more intently than they watched the larger one from a few days ago. That should strike you as strange. The reason it is true is the reason this entire video exists, and we are going to earn our way to it carefully. Let me give you the shape of what happened, because the sequence matters more than any single moment inside it. This flare did not erupt out of a calm and quiet sun. It arrived at the very top of a staircase. Through the overnight hours, from the same spot came a run of smaller flares, one after another, each one a step higher than a truly quiet sun would ever produce. And riding out ahead of this morning's main event, instruments caught a particular kind of radio signature, a tone that sweeps downward in frequency over a matter of minutes. That downward sweep is not random. It is the sound, translated into radio, of a shock wave climbing outward through the sun's atmosphere, and a shock wave like that is very often driven by a physical thing being thrown off the sun, a cloud of its own outer atmosphere torn loose and launched into space. The measured speed of that shock was around 600 kilometers per second. In the time it takes you to read this sentence, something moving at that speed has crossed more distance than the width of a continent. So already, in the first minutes of this story, we have 3 facts stacked, one on top of another: a strong flare, a blackout that has already come and gone, and a fingerprint written in radio suggesting this flare may not have kept all of its energy to itself. Any one of those in isolation is an ordinary event on an active sun. It is the way they are arranged, and above all the place they came from, that had forecasters leaning toward their screens this morning instead of simply logging another flare and moving on. Because the place they came from is the part that changes everything. This morning's flare, and the staircase of smaller ones beneath it, and the radio fingerprint of a cloud thrown outward, all came from a single sunspot group that has spent the last 5 days doing something slow and quiet and, once you understand what you're looking at, genuinely unsettling. It has been turning, and what it has slowly turned to face, after days of pointing somewhere else entirely, is us. It helps to know that the R-scale does not stop at the 2 we got this morning. It climbs. An R1 is a minor event, a faint degradation you would only notice if you were listening carefully on the right band. An R2, today's level, is a moderate blackout lasting minutes across the sunlit side. Above that sits R3, a strong event that can black out high-frequency radio across an entire daylit hemisphere for something closer to an hour and start to degrade the low-frequency signals that some navigation systems lean on. Higher still, R4 and R5, the severe and extreme levels describe blackouts that swallow the sunlit half of the planet for hours at a stretch. Each rung up that ladder corresponds to a flare roughly 10 times more powerful than the rung below it. This morning we sat at R2. The title of this video is a promise that forecasters spent the day taking seriously, which is that this same region has a real and measurable chance of climbing that ladder further and doing it while pointed at us. Keep the ladder in your mind because we are going to be climbing it in your imagination before we are done. We are going to take this apart piece by piece, because the details are where the real story lives, and because there is a version of this circulating online at this very moment that gets the drama exactly right and the physics badly wrong. But before any of that, you need to feel the basic asymmetry at the heart of the whole thing. The blackout this morning was real, and it is already over. The thing that would actually threaten the machines, your daily life quietly depends on, has not happened, and may not happen at all. The danger here is not a wound that has been dealt. It is a loaded possibility, sitting near the centre of the sun's disk, pointed in our direction, with the odds ticking a little higher every day it lingers there. And the single question hanging over the entire next few days is whether the calm you are feeling right now is safety, or simply the travel time of something that has already left. Part 2. The Staircase of Fire. To understand why a not-quite-record flare had forecasters on edge this morning, you have to understand what came before it, because on the sun, the flares that matter most are rarely the ones that arrive alone. Through the overnight hours, that same region fired a sequence of moderate flares in close succession. In the language of the scale, they went an M1.9, then an M1.0, then an M1.8, 3 flares of the M class packed into roughly a 10-hour window. Taken individually, flares of that size are unremarkable. An M1 sits at the very floor of the moderate category, the kind of event that happens many times over during an active stretch, and barely leaves a mark beyond a brief shimmer of interference on the daylight side of the planet. If you had been shown only one of them, you would have shrugged, and you would have been right to. Forecasters would have logged it and gone back to their coffee. But they did not come one at a time, and they did not fade. They came in a row from a single source, across a single night, and then the sequence did not level off the way a dying region's output does. It climbed. From flares near the bottom of the M class, the region leapt to an M6.9 by mid-morning, a flare very nearly 4 times as strong as the largest of the overnight events. That is not noise on a chart. That is a direction of travel. And a rising trend of flares from one region is the single pattern that flare forecasters treat as a genuine warning, rather than a passing curiosity. To feel why, it helps to borrow an idea from a completely different part of this channel's world, the ground beneath our feet. When seismologists watch a swarm of small earthquakes cluster in one place, most of the time it means nothing, and the swarm simply fades back into the background. But the reason anyone watches a swarm at all is that, occasionally, it is the crust telling you that stress is accumulating faster than it is being released, and that a larger break may be coming. A run of solar flares carries the same ambiguity and the same stakes. Each flare is a release of magnetic tension inside the region's field. When the flares grow instead of shrink, it usually means the region is winding tighter than it is unwinding, that whatever process is pumping energy into that tangle of magnetism is, for now, winning against everything trying to bleed it away. A region that is winning that argument is a region capable of the single largest kind of release the sun produces. I want to be careful here, because this is precisely the point where excitement tends to sprint out ahead of the evidence, and that is not how we do things. A rising sequence of flares raises the odds of a big one. It does not promise one. Plenty of regions climb a staircase exactly like this one, and then, at the top, simply stop. The tension quietly leaking away, the whole threat rotating harmlessly off the edge of the sun over the following week. The honest word is not certainty. The honest word is loaded, and a loaded region earns your attention precisely because you cannot know in advance which way it is going to break. What allows a sunspot to climb a staircase like that at all comes down to the architecture of its magnetic field, and this is where the region at the centre of our story earns its dark reputation. Sunspots are not really holes, and they are not really surface stains. They are places where bundles of magnetic field generated by the churning dynamo deep inside the sun have forced their way up through the surface and, in doing so, have choked off the normal upward flow of heat beneath them. Starved of that heat, the patch cools, and because it is cooler than everything around it, it looks dark to us by contrast. A simple sunspot is a tidy object. One bundle of field coming up, a matching bundle going back down, like the two ends of a single bar magnet pushed through a tabletop. Tidy spots produce small flares, if they manage to produce any flares at all. The dangerous ones are anything but tidy. Forecasters describe the magnetic complexity of a sunspot group using a short vocabulary of Greek letters, and the term that makes every space weather forecaster sit up straight is delta. A delta configuration means that opposite magnetic polarities, the equivalent of a north pole and a south pole, have been crushed so close together that they share a single dark core jammed up against one another with no clean boundary in between. That arrangement is not stable, and it is not meant to last. It is a magnetic knife edge. The field lines trapped between those opposing polarities are forced into a state of tremendous stress, twisted and sheared and storing energy the way a wound spring or a bent branch does, quietly, until it cannot hold anymore. When those stressed field lines finally snap and reconnect into a lower energy shape, the energy that pours out of that rearrangement is what we observe, 8 minutes later, as a flare. Almost every one of the very largest flares in the modern record has come from a region carrying a delta. The region we are watching this morning is exactly that kind of region. Its full classification is beta-gamma delta, which is forecaster shorthand for about as tangled, as sheared, and as tension-loaded as a sunspot group is capable of being. This is not a simple spot that got lucky with a single flare. It is a large, complicated, magnetically violent structure that has been producing flares for days because producing flares is simply what a structure like that does. The overnight staircase was not a coincidence. It was the sound of a knife edge working itself steadily looser, one release at a time, and then this morning cutting deeper than it had all night long. It is worth pausing on what those letters and numbers actually measure, because the scale is stranger than it looks, and it is about to do some heavy lifting for us. Flares are ranked by the peak brightness of the X-rays they pour out, and the classes C, then M, then X are not evenly spaced. Each letter marks a jump of 10. An M flare is 10 times more powerful than a C flare, and an X flare is 10 times more powerful again. Within a single letter, the number just fills in the gap. So an M2 is twice an M1, and an M6.9 is nearly 7 times the floor of the M class. That means this morning's flare, an M6.9, is already sitting close to the ceiling of its category. Nudge it a little higher and it crosses into X territory, the top class, the one with no letter above it. Put another way, this morning the sun fired a shot that landed about 7/10 of the way from the bottom of the moderate class to the threshold of the extreme one. It did not cross that threshold, but it demonstrated in the plainest possible terms that this region is operating in the neighbourhood where crossing it becomes a real possibility, and this is where the flares connect back to the reason any of it should matter to a person standing on the Earth with a phone in their pocket and a power grid feeding their home. A region like this is dangerous in proportion to two separate things: how much energy it is capable of releasing, and where it happens to be pointing at the moment it releases it. We have just spent this part on the first of those, the raw capacity for violence. The second, the aim, is where this entire story pivots, because this particular knife edge has not been holding still. For the last 5 days it has been slowly rotating across the face of the sun. To understand what that rotation means and why it turns a smaller flare into a bigger story, you have to know where this region was when it first announced itself, and what it did the last time we stood here looking straight at it. Part 3. The region with a history. If the name of this region sounds familiar to you, it should, because we have stood in this exact spot before, staring at this same wound on the sun, and the last time we did, it fired the single biggest flare of the entire solar cycle. Cast your mind back 5 days, to our video from the 20th of August. The region we are watching this morning had only just rotated into view around the eastern edge of the sun, and almost the instant it appeared it announced itself with an enormous flare, an M8.1, the strongest single flare anyone had recorded in this cycle up to that point. We spent that entire video on it, and if you were with us, you will remember the strange twist sitting right at the centre of the story. That giant flare, for all its raw power, was aimed almost entirely away from us. The region was perched near the very edge of the sun's visible disk, out on what astronomers call the eastern limb, and from that position, anything it hurled outward went sideways, flung across the solar system on a path that would miss the Earth by an enormous margin. We had a monster on our hands, and we had the plain good luck that the monster was facing the wrong way. Then, the very next day, we came back because the region refused to settle down. In the video from the 21st, we walked through a run of 6 flares of the M class in under 2 days from that same spot, and we drew you a window, a stretch of days during which the sun's own rotation would carry this region across the face of the disk and into the zone where its output would begin to matter for us directly. We even put dates on it. We told you the region would rotate into a position from which it could actually strike the Earth somewhere in the range from the 23rd to the 27th of August. Today is the 25th. We are standing inside the very window we drew for you 5 days ago, and the region has done precisely what a loaded region does inside a window like that. It has fired. So let me state the identity of this thing as plainly as I can, because everything downstream depends on getting it right. This is not some new region that materialized overnight. This is a known, tracked, named troublemaker, catalogued by forecasters as Active Region 4513, and it has been the most dangerous single feature on the entire sun for the better part of a week. It arrived complex, it arrived violent, and it has stayed both. The one thing that has changed, the single variable that has moved, is its position, and that one moving variable is the whole reason the M6.9 this morning is a larger story than the M8.1 was 5 days ago, even though the M8.1 was and still is the bigger flare. Let that invert your instincts for a moment, because it should. Bigger is not, on its own, the thing to be afraid of. A colossal flare aimed away from you is a light show, something for the instruments to admire and the record books to note. A somewhat smaller flare from the same violent region, now swinging around to aim at you, is a threat. The sun did not have to become more powerful this week in order to become more dangerous to us. It only had to turn, and it has spent 5 patient days turning. I want to make the physical reality of this region concrete, because it is far too easy to talk about sunspots as marks on a chart and lose all sense of the scale of the thing. Active Region 4. 513 is a structure larger than the Earth, a knot of magnetism many thousands of miles across, in which fields of opposite polarity are pressed together along that delta knife edge we spent the last part describing. It is storing energy that has to go somewhere. When it releases a fraction of that energy as a flare, the light from that release, the X-rays and the extreme ultraviolet, crosses to us in 8 minutes and does exactly what it did to the radio this morning. But a large enough release does not stop at light. It can tear a piece of the sun's own outer atmosphere loose, a cloud of magnetized plasma weighing billions upon billions of tons, and fling it outward into the solar system. Whether that cloud eventually strikes us or sails past us comes down, once again, to which way the region was facing at the instant it fired. 5 days ago, when the region sat out on the limb, the answer was simple: facing away. This morning, with the region marching toward the centre of the disk, the answer is beginning to shift toward the far more uncomfortable one: facing us. And that radio fingerprint that rode out ahead of this morning's flare, the downward sweeping tone at around 600 kilometers per second, is the signature of precisely that kind of cloud being thrown off. What we cannot yet say with any confidence is where that cloud is actually headed. That is one of the threads left dangling over the next several days, and we will come back to it in detail because it matters enormously, and because the honest answer at this moment is that we do not fully know, and anyone who tells you they do is selling you something. It is worth being precise about what that cloud actually is, because almost everything that could go wrong in the coming days depends on it. When a region's magnetic field snaps and reconnects violently enough, it does not just flash. It can eject a great bubble of the sun's outer atmosphere, its corona, a tangle of charged gas and embedded magnetic field that scientists call a coronal mass ejection. These are not small. A single one can carry a mass measured in the billions of tons and span a distance many times the width of the Earth by the time it reaches us. And unlike the flare's light, which arrives in 8 minutes and is gone, the cloud is slow. It has to physically cross the 93 million miles of empty space between the Sun and the Earth, and even the fast ones take somewhere between 1 and 3 days to make the trip. That delay is the reason this story has a future tense at all. The light already came and went this morning. The cloud, if there is one aimed our way, is still out there, somewhere on the road, and it does not announce itself until it arrives. The downward sweeping radio tone is our earliest and most uncertain hint that a cloud left at all. What it cannot tell us yet is the address on the envelope. What we can say with confidence is the trajectory of the region itself, and it has been relentless. It rounded the eastern edge of the sun as a monster pointed away from us. It has been marching steadily toward the middle of the disk ever since, day after day, carried by the sun's roughly month-long rotation. And the middle of the disk, the point dead centre on the face the sun turns toward the Earth, is the single most dangerous place a region like this one can possibly be. To understand why that specific position matters so much, and why forecasters have a quiet, almost superstitious phrase for it, we need to talk about the sweet spot and about what it means for a violent region to finally arrive there and turn its full attention toward home. Part 4. The Sweet Spot. There is a position on the sun that space weather forecasters watch the way a chess player watches a square in the centre of the board, and this morning active region 4513 moved onto it. To see why that square matters, you have to picture the sun not as a flat disk hanging in the sky, but as what it actually is, a rotating ball. It spins, roughly once a month as seen from Earth, carrying its features from the eastern edge across the middle and off the western edge, the way markings on a slowly turning globe travel from one side to the other. A sunspot near the eastern edge is like a headlight angled off to the side of a dark road. It is pointed across your path, not down it. A sunspot in the dead centre of the disk, facing us squarely, is a headlight aimed straight into your eyes. Same lamp. Completely different consequence for the person standing in front of it. 5 days ago, this region was that headlight angled off to the side. When it fired its enormous M8.1, the region sat far out on the eastern edge of the disk, at a position forecasters write as roughly 4 degrees north and 85 degrees east. 85 degrees east is almost all the way to the rim. From there, anything the region threw off went sideways, out across the solar system, on a heading that had nothing to do with Earth. Then the sun did what the sun always does. It turned. By yesterday, the region had marched inward to about 10 degrees east, close to the central line of the disk, quieter for a stretch, firing smaller flares while it moved. And this morning, when it let loose the M6.9, it sat at roughly 3 degrees north and 5 degrees east. 5 degrees east is, for all practical purposes, dead centre. The headlight is now pointed very nearly straight at us. This is the revelation the whole story has been walking toward, so let me say it as plainly as I can. The thing that made this morning more dangerous than 5 days ago was not a change in the sun. It was a change in the aim. The region did not grow more violent. If anything, This morning's flare was smaller than the one that opened the whole saga. What changed is that the violence is now facing home. For 5 days, we have been watching a loaded weapon slowly rotate until the barrel came around to point in our direction. And this morning we heard it go off with a round that, this time, did not miss by design. It missed, if it missed at all, only because we do not yet know whether it fired a cloud on a path to reach us. That central region of the disk has an unofficial name among the people who do this work. They call it the sweet spot, or the strike zone, and the reason is a matter of simple geometry. A coronal mass ejection tends to travel outward roughly along the line from the centre of the Sun through the region that launched it. When the launching region is dead centre on the disk, that line points straight down the 93 million mile corridor to Earth. A cloud thrown from the centre of the disk is a cloud thrown at us. A cloud thrown from the edge sails off to the side. So the same eruption, the same billions of tons of magnetized plasma moving at the same speed, is either a direct hit or a complete non-event depending entirely on where on the disk the region happened to be when it let go. This region has spent 5 days walking into the one position where the answer flips from non-event to direct hit. There is a second, subtler piece of geometry that matters here, and it concerns not the cloud, but the particles. When a flare accelerates atomic particles to enormous speeds, those particles do not travel in straight lines through space. They spiral along the Sun's magnetic field, which winds outward from the Sun in a great curve, like water spraying from a turning sprinkler. Because of the way that curve bends, the magnetic field lines that connect most directly back to the Earth actually route into the Sun a bit west of centre, not at the exact middle. So as this region continues its march and crosses from the centre toward the western half of the disk over the coming days, it will move into the zone that is best connected to us for particle radiation, even as it begins to slide out of the best zone for a direct cloud strike. The threat does not simply switch off when the region passes the middle, it changes character. For the next couple of days it sits in the worst position for a cloud aimed at Earth, and then it rotates into the worst position for a wave of radiation aimed at Earth. There is no comfortable moment in the near future. There is only a handoff from one kind of exposure to another. It is worth walking the rotation day by day, because seeing the motion is what makes the threat feel real rather than abstract. 5 days ago, the region was at about 85 degrees east, hugging the rim, a monster in profile. Over the following days, the Sun's rotation carried it inward at a steady pace, a dozen or so degrees each day, the way a mark on a slowly turning wheel travels from the edge toward the centre. By yesterday, it had reached about 10 degrees east, and it spent that stretch of the journey comparatively subdued, throwing smaller flares, almost as if it were catching its breath for the crossing. And then this morning, having arrived at roughly 5 degrees east, essentially the centre line, it fired the M6.9, read that sequence as a whole, and it tells a story that no single frame captures. The region did its quietest work while it was still turning into position, and then, the moment it reached the seat with the clearest shot at Earth, it spoke up again with the biggest flare it had produced in days. Whether that timing is meaningful or coincidental, no one can say, but it is exactly the sequence that makes forecasters uneasy, a violent thing going quiet as it takes aim and then firing once it is lined up. I do not want to overstate this, because overstating it is exactly the trap this topic sets. The region being centred does not mean a strike is coming. It means that if the region fires something large in the next couple of days, the geometry is as unfavourable for us as it gets. Aim is a multiplier, not a trigger. It turns a possible flare into a possibly consequential one. Whether that possibility is realised still depends on whether this knife edge of a region actually produces a large enough eruption while it lingers here, and that is precisely the thing nobody can promise in advance. So we now have 2 of the 3 pieces that make forecasters nervous. We have a violent Delta-class region, capable of the largest flares the Sun produces, and we have that region parked in the sweet spot, aimed at us for the next couple of days. The third piece is the one that turns geometry into probability, the cold arithmetic of how likely all of this actually is, and it comes down to a single, sobering pair of numbers that forecasters attach to this region this morning. Part 5. 1 in 10. Every morning, the people who forecast space weather publish a set of probabilities, and this morning the numbers attached to active region 4513 were the kind that make you read them twice. They put the daily chance of an M-class flare from this configuration at around 45%, and the daily chance of an X-class flare at around 10%. Sit with that second number for a moment. 10%. 1 in 10. On any given day right now, there is roughly a 1 in 10 chance that this region produces a flare of the very top class, the extreme category, the one we have been climbing toward this whole time, and it would do it while sitting in the sweet spot aimed at us. Now, I want to handle those numbers honestly, because honesty about probability is where a lot of coverage of this stuff falls apart. 1 in 10 is not a prediction that it will happen. It is much closer to a prediction that, on most days, it will not. If you flip that around, a 10% daily chance of an X-flare means a 90% daily chance of no X-flare. The single most likely outcome tomorrow, and the day after, is that this region does not fire an X. That is the truth, and anybody telling you an extreme flare is guaranteed is ignoring the same numbers they are quoting. This region could just as easily spend the next 3 days throwing moderate flares, sliding toward the western edge, and rotating off the disk, having never crossed into the top class at all. That is a completely ordinary way for a story like this to end. But here is why forecasters do not shrug at a 1 in 10 day. Probabilities compound. That 10% is a daily figure, and the region is going to sit in a threatening position not for 1 day but for several. A 10% chance today, and roughly again tomorrow, and roughly again the day after, stacks into a meaningfully larger chance that somewhere across that window at least one big flare occurs. Rolling a 10% event once is unlikely. Rolling it every day for the better part of a week is how unlikely things quietly become likely, and the whole time those dice are being rolled, the region is aimed at the sweet spot. So the honest framing is not that an extreme flare is coming, it is that the odds of one somewhere in this window are high enough, and the consequences of one aimed at us serious enough, that no responsible forecaster is going to look away until the region rotates out of range. This is the right place to confront a number that could otherwise mislead you, because it goes straight to the heart of what this region is and is not. This morning's flare was an M6.9. 5 days ago, the opening flare was an M8.1. On the scale we talked through earlier, the M8.1 is the larger of the two. It is not close, in the way that matters, but it is real, and it means something important. The biggest flare this region has produced so far did not happen this morning. It happened 5 days ago, when the region was still on the limb facing away. So no, this morning's flare is not a new record for this region, and you should be suspicious of anyone who tells you it is. The M6.9 is not the peak of anything. It is a data point in a pattern, and that is exactly why it matters more than its size alone would suggest. This is not a story about a single record-breaking flare. If it were, the M8.1 from 5 days ago would be the headline and this morning would be a footnote. This is a story about a pattern and a position. The pattern is a violent region that keeps firing and, over the last day, has been firing bigger. The position is the sweet spot. A region that has already demonstrated it can reach into the upper M class and even brush the neighbourhood just below X, is a region for which a 1 in 10 daily shot at an X-flare is not an abstract statistic. It is a straightforward extrapolation of what it has been doing all week. The M6.9 is the region reminding everyone, from the most dangerous seat on the disk, exactly what class of object it is. It is worth knowing where a number like 10% even comes from, because it is not a guess pulled from the air. Forecasters build these daily probabilities partly from the long historical record of how often regions of a given size and magnetic complexity have gone on to produce a large flare, and partly from what this specific region has been doing over the preceding days. A large beta-gamma-delta region that has already been firing M-class flares is, historically, exactly the kind of setup that has produced X-flares often enough to put the daily odds in the range we're seeing. In other words, the 10% is the region being measured against every region like it that came before, and the verdict of that comparison is that roughly 1 day in 10, a configuration like this one crosses into the top class. That is not fortune-telling. It is the accumulated memory of a century of watching the sun applied to the object sitting in the sweet spot this morning. Let me connect that back to the machines, because the abstraction of flare classes can make you forget there is a reason to care. An M-class flare, like this morning's, gives you a radio blackout measured in minutes on the daylight side. That is an inconvenience, a hazard for the specific systems that live on those bands, but not a civilizational problem. An X-class flare is a different animal. At the low end it means a strong radio blackout across a whole hemisphere for something closer to an hour, and degraded navigation signals on top of it. At the high end, the very largest X-flares can black out the sunlit half of the planet for hours, and, If they come with a fast cloud aimed at us, they are the opening act of the kind of geomagnetic storm that reaches all the way down to the power grid. The distance from an M6.9 to a Sirius X flare is not large in absolute terms. It is one more step up a ladder this region has been climbing all week, and the region is standing on that ladder in the one spot where a step up would be aimed directly at us. Which brings us to the strangest part of this entire morning, the part that does not fit the story you would expect. Because if all of this is true, if a violent region is sitting in the sweet spot firing flares with a 1 in 10 daily shot at an extreme event, you would expect the instruments here on Earth to be screaming, and they are not. They are at this very moment almost perfectly calm. Part 6. The quiet that doesn't make sense. Here is the fact that does not seem to belong in this story. Right now, as the sun sits there loaded and aimed, the magnetic field of the Earth is quiet. Not slightly disturbed. Quiet. There is a number for the state of Earth's magnetic field, an index that runs from 0 to 9, and measures how disturbed our planet's magnetism is at any given moment. Forecasters call it the KP index. 0 and 1 mean dead calm. A reading of 5 is the threshold where we start calling it a geomagnetic storm. 9 is the top of the scale, the realm of the great historic storms. This morning, with a violent region in the sweet spot and an M6.9 fresh off the sun, the KP index is sitting at around 2. That is firmly in the calm range. There is no geomagnetic storm in progress. There is no official storm watch posted for today. There is no confirmed cloud of plasma on a certain path to hit us. By every instrument that measures the state of the space immediately around the Earth, this is a quiet day. How can both things be true at once? A loaded, aimed, actively firing region on the sun, and a calm and untroubled Earth? The answer is one of the most important ideas in this entire subject, and once you understand it, the eerie stillness stops feeling like reassurance and starts feeling like something else entirely. It comes down to the fact that a solar flare does not send us one thing, it sends us several, and they travel at wildly different speeds. The first thing to arrive is the light, the X-rays, and the extreme ultraviolet, and light is the fastest thing there is. It crosses from the sun to the Earth in about 8 minutes, which is why this morning's radio blackout happened essentially the instant the flare peaked. That part of the event is not a warning of something to come. It is the fast messenger, and it has already been and gone. The blackout is over because the light that caused it stopped arriving the moment the flare faded. But the light is not the part that reaches the power grid. That job belongs to the slow messenger, the coronal mass ejection, the physical cloud of plasma we talked about earlier. And the cloud is enormously slower than the light. Where the light takes 8 minutes, the cloud takes between 1 and 3 days to cross the same gap, because it is matter, not radiation, and it has to plough its way through the solar wind the whole distance. So when a region in the sweet spot fires a flare with a cloud attached, this is exactly what you would expect to see on Earth. An immediate radio blackout from the light, followed by a day or more of complete calm, followed only then by the arrival of the storm. The quiet is not the absence of danger. The quiet is the interval between the messengers. Let me put that as plainly as I can, because it is the pivot of the whole video. The calm you are feeling right now is exactly what the beginning of a large event would feel like, and it is also exactly what a complete non-event would feel like. From the ground, in the first day, the two are indistinguishable. If this morning's flare launched a fast cloud straight at us, the Earth would sit quiet for a day or so and then light up. If this morning's flare launched nothing our way, the Earth would sit quiet and simply stay quiet. Same silence. Two completely different futures, and we are living inside the exact stretch of time when you cannot yet tell which one you are in. It helps to put actual thresholds on that quiet, because the numbers make the stakes concrete. The disturbance scale runs from 0 to 9, and a reading of 5 is where a storm officially begins. The level forecasters label a minor storm on their own 1 to 5 storm scale. As the reading climbs, the aurora climbs down in latitude to match it. A minor storm nudges the northern lights to the top of the map. A strong storm can drag them into the middle latitudes. A great storm, the top of the scale, can push them into the southern reaches of the United States, which is the visible signature of a magnetic field being shaken hard enough to reach the power grid. This morning that reading is sitting at about 2, not 4, edging toward a storm, not 3, elevated and worth watching. 2, which is the number for an ordinary untroubled day. Everything we have described, the loaded region, the sweet spot, the near-X flare, is happening while the one instrument that would register an actual attack on the Earth reads a flat and unremarkable 2. That is not a contradiction to be explained away. It is the entire point. The gap between what the Sun is doing and what the Earth is feeling is the gap that the slow messenger has not yet crossed. Now, I want to be careful and fair, because the honest reading of the data today leans toward the calmer of those two futures, not the dramatic one. As of this morning, forecasters have not issued a geomagnetic storm watch. The absence of a watch is meaningful. It reflects the current judgment that there is no confirmed, fast, Earth-directed cloud bearing down on us from this morning's flare. If a big obvious halo cloud had been seen erupting straight at Earth, the watches would already be up. They are not, so the most likely path, based on what is actually measured right now, is that today's flare was serious for the radio and not the opening move of a grid-level storm. That is the responsible thing to say, and I am saying it. But, and this is the whole reason we are here, the region is not finished. It stays in the sweet spot for another couple of days. The staircase of flares has been climbing, not fading. And the one thing the quiet cannot tell you is what the region does next, while it is still aimed at you. The calm on the instruments this morning is a report on what has already left the Sun. It is not a forecast of what the region fires tomorrow, from the same loaded seat, with the same 1 in 10 daily odds of reaching the top class. So the silence is real, and it is also, in a specific and unsettling way, uninformative about the thing we actually want to know. Which raises the question we have been circling since the first minute. If a big one did come, if this region fired an extreme flare with a fast cloud while pointed at us, what would actually happen? What exactly is at stake on the other end of that 93 million mile corridor? To answer that, we have to follow the messengers all the way to the ground in order and see what each one touches when it arrives. Part 7. 8 minutes, then hours, then days. If active region 4513 fires the big one while it sits in the sweet spot, the event would not reach us as a single blow. It would arrive in waves, and the waves are separated in time by hours and days, each one carrying a different kind of danger to a different set of machines. To understand what is truly at stake, you have to stop thinking of a solar storm as one thing, and start thinking of it as a convoy, strung out along the road from the Sun, with the fast vehicles arriving long before the slow ones. The first wave is the light, and we've already met it, because it is the wave that hit us this morning. The X-rays and the extreme ultraviolet cross the gap in 8 minutes and go to work on the top of the atmosphere, thickening the ionosphere and swallowing high-frequency radio on the daylight side. For an ordinary M flare that is the whole story, a blackout measured in minutes. For a great X flare, the same mechanism runs harder and longer, blacking out radio across an entire sunlit hemisphere and reaching down to disturb the low-frequency signals that some navigation and timing systems depend on. But the important thing about the light is that it arrives first, and it warns of nothing, because it moves at the same speed as our ability to see the flare that made it. By the time you know the light has come, everything else in the convoy is already somewhere behind it, and you cannot yet see how far. The second wave is radiation, and it is faster than most people expect. When a flare and its erupting cloud accelerate atomic particles, mostly protons, to a large fraction of the speed of light, those particles can begin sleeting past the Earth within tens of minutes to a few hours. This is the wave that does not care about the daylight side or the night side, because these particles come funneling in along magnetic field lines and rain down hardest over the poles. It is a radiation storm, and its victims are not radios but living tissue and delicate electronics. Astronauts, especially any beyond the shelter of the Earth's magnetic field, feel this one first, and worst. Airline crews and passengers on the high polar routes take a measurably elevated dose, which is why airlines reroute flights away from the poles during strong events, and the satellites we all depend on can have their electronics scrambled or their sensors blinded by the particle bombardment. We are going to spend the next part on this wave, because it is the one people understand the least, and it is the one that would arrive soonest if this region fires large. The third wave is the slow one, the cloud itself, the coronal mass ejection, and it is the wave that reaches all the way down to the ground. It takes its 1 to 3 days to cross the gap, and when it arrives, It does not black out radio or irradiate astronauts so much as it grabs the Earth's entire magnetic field and shakes it. That shaking is what we call a geomagnetic storm, and a changing magnetic field, by a law of physics as old and reliable as electricity itself, induces electric currents in anything long and conductive lying underneath it. The longest, most conductive things we have built are power lines and pipelines and undersea cables. This is the wave that can push currents into a power grid that the grid was never designed to carry. We will follow it to the transformer in 2 parts' time, and there is a fourth effect, quieter than the others, that rides along with the storm. The same energy that lights up the aurora also heats and puffs up the upper atmosphere, and a puffed-up atmosphere reaches higher, thickening the thin air that low-orbiting satellites fly through. More air means more drag, and more drag means satellites sink faster than expected and occasionally are lost. In an age when there are more objects in low orbit than at any time in history, this once obscure effect has become a live commercial hazard, and we will come back to it as well. Picture the timeline concretely, because the spacing is the whole point. Imagine this region fired its great flare at noon on some future day. By about 8 minutes past noon, the radio would already be blacking out on the daylight side, the fast messenger arriving before the news of the flare could reach anyone by any other means. Within the next hour or two, if the flare accelerated a strong burst of particles, the radiation storm would begin to register, sleeting in over the poles, sending satellite operators to their checklists and airlines to their maps. And then, for a day, or 2, or nearly 3, there would be nothing new. The Earth would sit in that strange suspended calm, the flare long over, the radio recovered, the instruments settling back toward quiet, while the slow cloud ground its way across the gap. Only at the end of that wait, without further warning to most of the world, would the cloud arrive and the geomagnetic storm begin, and the aurora spill south, and the currents start to creep into the long wires. One event. 3 arrivals, spread across 3 days. That stretched-out shape is exactly why a single quiet morning tells you so little, because the quiet is built into the physics of how the convoy travels. So hold the shape of the convoy in your mind, because it is the frame for everything that follows. Light in 8 minutes, radiation in minutes to hours, the cloud and the geomagnetic storm in 1 to 3 days. Atmospheric drag building over the days that follow. This morning only the first vehicle arrived, and it was a moderate one. The entire tension of the next few days is whether this region from the sweet spot sends the rest of the convoy after it. Let us follow each vehicle to its destination, starting with the one that would arrive soonest and that most people never think about at all, the radiation. Part 8. The radiation that follows the light. The wave of the convoy that would arrive soonest after the light, and the one almost nobody outside the field thinks about, is a flood of atomic particles moving at a large fraction of the speed of light, and it is the one that turns a solar storm from a problem for machines into a problem for people. When a large flare erupts, and especially when it drives a fast cloud outward, it acts like an enormous particle accelerator, whipping protons and other charged particles up to speeds that let them cross the space between the Sun and the Earth in as little as tens of minutes. Scientists call these solar energetic particles, and a heavy influx of them is called a radiation storm, measured on its own scale that runs, like the others, from 1 to 5. Because these particles are electrically charged, they follow the Earth's magnetic field down toward the poles, which is why the effects concentrate at high latitudes and over the polar routes rather than uniformly across the globe. Consider who is standing in the path of that wave. The most exposed human beings during a strong radiation storm are astronauts, and their vulnerability depends entirely on where they are. A crew aboard a station in low orbit still has most of the Earth's magnetic field arching protectively above them, and during strong events such crews are sometimes directed to move into the most shielded part of their spacecraft and wait it out. But a crew beyond that magnetic shelter, out on the way to the moon for instance, has no such umbrella. For them a severe radiation storm is not an inconvenience. It is a genuine medical hazard, a dose of radiation that has to be measured and managed, and in the worst cases sheltered against with whatever mass the spacecraft can put between the crew and the Sun. As humanity begins once again to send people beyond low orbit, this wave of the convoy stops being an abstraction and becomes one of the central design problems of deep space travel. Closer to home, the same particles reach down into the altitudes where aircraft fly, particularly over the poles where the magnetic field funnels them in. The radiation dose to passengers and crew on a single flight is not dangerous in the way a reactor accident is dangerous, but it is real, it is measurable, and it accumulates for the crews who fly those routes for a living. That is why, during strong radiation storms, airlines will move flights off the high polar routes and onto lower latitude tracks, accepting the extra fuel and time as the cost of keeping the dose down. A solar storm, in other words, can quietly rewrite the map of the world's air traffic for a day, and most of the passengers rerouted never know why their flight took the long way around. And then there are the satellites, which take this wave the way a windshield takes a sandstorm. High-energy particles slamming into a spacecraft can flip the bits in its memory, corrupt its data, confuse its star trackers so it loses track of which way it is pointing, and over time degrade the solar panels that keep it alive. A single particle striking the wrong circuit at the wrong moment can cause a glitch, a reboot, or, occasionally, permanent damage. Multiply that by the thousands of satellites now threaded through orbit, carrying the navigation, the communications, the imaging, and the timing signals that modern life quietly runs on, and you begin to see why a radiation storm is not just an astronomer's curiosity. History has already handed us a warning about this particular wave, and it is one of the great near misses of the space age. In early August of 1972, in the narrow gap between two of the crewed missions to the Moon, the Sun produced an enormous and unusually fast eruption, and with it a fierce radiation storm. No astronauts were in deep space at the moment it struck, but the missions had put crews on the lunar surface only months before and would again only months later. An analysis afterward concluded that a crew caught out on the Moon, beyond the Earth's magnetic shelter, during that particular storm could have received a radiation dose serious enough to cause real harm. It is one of the luckiest pieces of timing in the history of spaceflight, a lethal wave passing through the exact window when nobody was standing in it. That old storm is the reason radiation is not treated as a footnote. It is the wave that would arrive first and warn us least, and it is the one that turns the emptiness beyond low orbit from a frontier into a shooting gallery whenever a region like the one we're watching decides to fire. The mechanism by which these particles wreck electronics is worth picturing, because it is almost absurdly small and almost absurdly consequential at once. A single charged particle, moving fast enough, can strike a microchip and dump just enough energy in just the wrong spot to flip a bit, to turn a 1 into a 0 in a satellite's memory or its guidance computer. One flipped bit can be a harmless glitch, or it can be a corrupted command, a spacecraft that suddenly does not know which way it is pointing, a reboot at the worst possible moment. Multiply one particle by the sleeting flood of a real radiation storm, and multiply that by the thousands of spacecraft now threaded through orbit, and you begin to see how a wave made of individual particles too small to imagine becomes a threat to the machinery a planet runs on. I want to keep tying this back to where we actually stand this morning, because it would be easy to let all of this tip into fear, and fear is not the point. As of right now, there is no radiation storm in progress. The proton levels around the Earth are at background. This entire wave is, at this moment, hypothetical. It is what would follow if this region fires a large enough flare from the sweet spot in the next couple of days, and it is precisely the reason forecasters are watching so closely, because unlike the slow cloud, this wave gives you almost no warning. It arrives on the heels of the light. If the big flare comes, the radiation is not days away. It is minutes to hours away, which is exactly why the region sitting loaded in the strike zone, with a 1 in 10 daily shot at the top class, is not a threat you can afford to look away from and check on next week. But the radiation, for all its speed, is not the wave that reaches the power grid. That job belongs to the slow one, the cloud, and to understand what it could do, we have to follow it all the way down to the machine that quietly holds modern civilization together. Part 9. When the cloud finally arrives. The slowest vehicle in the convoy is the one that can do the most damage on the ground, and following it to its destination means following it all the way down to a device most people have never thought about and cannot live without, the electrical transformer. When the coronal mass ejection finally arrives, a day to 3 days after the flare, it slams into the Earth's magnetic field, and if the cloud's own magnetic field happens to be oriented opposite to ours, the two link up and the cloud pours its energy into our magnetic environment. The field that surrounds the planet, normally a steady and reassuring thing, begins to buckle and heave. This is the geomagnetic storm, and its severity is measured on a scale, once again from 1 to 5, that tracks how violently our magnetism is being shaken. A minor storm brings the aurora a little farther south and does little else. A great storm can push the northern lights down to the latitudes of the southern United States, and far more consequentially, can reach into the power grid. The mechanism is worth understanding because it is both simple and unsettling. There is a principle in physics, discovered in the 19th century, that a changing magnetic field creates an electric current in any conductor sitting within it. It is the principle behind every electric generator on Earth. During a geomagnetic storm, the magnetic field over whole continents is changing rapidly, and the Earth itself, along with everything conductive lying on it, sits inside that changing field. The result is that slow, powerful electric currents are induced in the longest conductors we have built, the high-voltage transmission lines that carry power across countries. These are called geomagnetically induced currents, and they are direct currents, flowing where the grid expects only alternating current. That distinction is where the danger lives. The great transformers at the heart of the power grid are built to handle alternating current, the kind that reverses direction many times a second. When a slow, one-directional current from a geomagnetic storm flows through them, it pushes the transformer's magnetic core into a state it was never designed for, a state called saturation. A saturated transformer runs hot, hums, draws power it should not, and can begin to cook itself from the inside. In a bad storm, transformers can be damaged or destroyed outright. And here is the part that keeps grid engineers awake. The largest transformers are not off-the-shelf items. They are custom-built, often overseas, weighing hundreds of tons, and they can take months or longer to replace. A storm that destroys many of them at once does not cause a blackout you fix by morning. It causes a hole in the grid that takes a very long time to patch. This is the deepest reason a violent region in the sweet spot matters. Not the radio blackout, which is over in minutes, not even the radiation, which threatens astronauts and satellites but leaves the ground largely alone. It is this, the possibility, however unlikely on any given day, that a large enough eruption aimed directly at us could push currents into the grid strong enough to damage the machines that the modern world cannot quickly replace. That is the tail end of the story that begins with a small radio blackout on a quiet morning. The M6.9 was the fast messenger, the light. The thing forecasters are actually watching for is whether the region sends the slow messenger after it, the one that ends at the transformer. We actually have a benchmark for the worst of it, and it comes from long before the power grid existed, which is part of what makes it so haunting. In early September of 1859, the Sun produced the most powerful geomagnetic storm in recorded history, an event now named after the English astronomer who watched the flare that caused it. The technology of the day was the telegraph, a web of wires strung across continents, and the storm reached into those wires with the same induced currents we have been describing. Telegraph operators reported sparks leaping from their equipment, paper catching fire, and most eerily, machines that kept sending and receiving messages even after their batteries had been disconnected, running on the current the storm itself was pushing through the lines. The aurora that night was seen almost to the equator, bright enough in places that people rose thinking it was dawn. In 1859, that storm was a curiosity and a spectacle, because there was almost nothing electrical for it to break. The unsettling question that hangs over the whole field is what that same storm would do to a civilization that has since wired itself into complete dependence on the grid, and the honest answer is that we have never found out because a storm of that size has not struck the modern world. The replacement problem is the part that turns a bad night into a bad year. The largest transformers on the grid are not spare parts sitting in a warehouse. They are custom designed for their specific place in the network, built to order, often on another continent, each one weighing hundreds of tons and taking many months, sometimes more than a year, to manufacture and deliver. In ordinary times, a utility might lose one now and then and swap it out with careful planning. A great storm that damaged many of them at once, across many regions simultaneously, would confront the world with a demand for these massive machines that the factories simply cannot meet quickly. That is why the serious worst-case studies talk about recovery times measured in months to years rather than hours. It is not that the storm itself lasts that long. It is that the holes it punches in the grid cannot be patched at the speed modern life assumes. now, I have to bring this back to reality, hard, because it would be easy to leave you picturing the lights going out, and that is not where the honest data points today. There is no cloud confirmed on its way to us right now. There is no storm watch posted. The grid is under no threat as I speak. Everything in this part is the answer to a conditional question. What would happen if this region fired large and aimed true? And the most likely outcome over the next few days remains that it does not. But conditionals are exactly what forecasters are paid to take seriously, because the cost of being wrong in the reassuring direction is so much higher than the cost of being wrong in the cautious one. And we do not have to imagine what the far end of that conditional looks like, because it has happened before, more than once, within living memory. To understand why a 1 in 10 day is taken so seriously, you have to see the nights the grid actually went down. Part 10. The Nights. The grid remembers. The reason a 1 in 10 day gets forecasters out of their chairs is not a theory or a computer model, it is memory. The grid has gone down from a solar storm before, more than once, and the people who run it have not forgotten what it looked like. Go back to the 13th of March, 1989. A large, complex region on the Sun had thrown a cloud of plasma toward the Earth, and when that cloud arrived, it triggered one of the most severe geomagnetic storms of the 20th century. Across the province of Quebec, the Great Transmission Network run by Hydro-Quebec was carrying power to millions of people on a cold, late winter night. As the storm reached its peak, geomagnetically induced currents came surging into that network from the shifting field overhead. Protective systems, seeing conditions they were never designed to interpret, began to trip, and then it cascaded. In the span of about 90 seconds, the entire Quebec grid collapsed. 90 seconds. Roughly 6 million people lost power, in some places for around 9 hours, in the dark and the cold, because of a cloud of gas launched from the sun days earlier, and a magnetic field that could not tell the difference between a normal night and an assault from space. Sit with the timescale of that, because it is the thing people always get wrong. The cloud took days to arrive, but once it did, the grid did not fail over hours, giving operators time to react and shed load and save their equipment. It failed in a minute and a half. That is the cruel signature of this hazard. The warning is measured in days if you can read it, and the collapse, when it comes, is measured in seconds. There is no slow slide you can catch in the act. There is a long quiet, and then there is a very fast fall. It is the same long quiet that sits over the Earth this morning, while a violent region stares at us from the centre of the Sun. The aftermath is worth dwelling on, because the 90 seconds were only the beginning. When the Quebec grid went down that morning, it took with it the heat, the light, and the machinery of a modern society in the depth of a Canadian winter. Traffic signals died. The underground transit in Montreal stopped. Schools and offices went dark. Airports lost equipment. Millions of people were left for the better part of a working day without the electricity that everything else quietly depends on, and the utility spent long afterward assessing damaged equipment and hardening the system against the next time. The financial cost ran into the hundreds of millions, but the number that lingers is not the money. It is the image of an advanced, wealthy, well-run society brought to a standstill for 9 hours by a cloud of gas that had left the sun several days earlier, on a morning that, until the final 90 seconds, would have felt exactly as ordinary as this one. That is the shape of this hazard, a long, unremarkable calm, and then a fall too fast to stop. Now push forward to late October 2003, to the run of storms that space weather people simply call the Halloween storms. Over about 2 weeks, the sun unleashed a barrage of enormous flares, including some of the most powerful ever recorded, and hurled cloud after cloud toward the Earth. The aurora, normally a polar spectacle, was seen at latitudes where most people have never witnessed it in their lives, pushing down into the southern United States and across southern Europe. But the storms did more than paint the sky. In Sweden, the city of Malmö lost power for about an hour when the grid was overwhelmed. In South Africa, transformers were damaged, some so badly they had to be replaced, in a country far from the poles that had assumed itself relatively safe. Aircraft were rerouted away from the polar corridors to keep radiation doses down. Satellites logged anomalies across every kind of orbit, and one Japanese Earth observation spacecraft was disabled entirely. The Halloween storms are the modern textbook case of what a sustained assault from an active sun actually does to a technological civilization spread out across a planet. And here is the detail from 2003 that speaks most directly to this morning. Those storms happened when the solar cycle was already past its peak and on the way down, in what scientists call the declining phase. The intuition that a sun on the downslope of its cycle is a safe sun is exactly the intuition the Halloween storms destroyed. Some of the most violent space weather of the entire space age came from a sun that was, by the simple count of its spots, supposedly winding down. We are right now in the declining phase of the current cycle. The region we are watching is firing from a sun that a naive glance would call past its prime. The Halloween storms are the reason no forecaster treats that as reassurance. I keep returning to the same point because it is the spine of this whole story, and here it takes on weight. Everything that happened over Quebec in '89 and across the world in 2003 began exactly the way this morning began, with a violent region and a flare, and crucially a cloud aimed at Earth. The difference between those catastrophic nights and an ordinary quiet week is not the existence of a dangerous region. Dangerous regions come and go all the time. The difference is whether the region, while pointed at us, fires something large enough with a fast cloud attached. That is the exact question hanging over active region 4513 for the next couple of days. We are not watching it because a storm is certain. We are watching it because we have seen, in living memory, what the far end of this looks like, and it looks like 6 million people in the dark in 90 seconds. But the grid is not the only thing the modern world has hung in the path of these storms. Since those older events, we have lofted a second, sprawling nervous system into the sky. Thousands of satellites threaded through low orbit, and it turns out they are vulnerable in a way that is newer, subtler, and in some ways even harder to defend, as we learned quite recently and quite expensively. Part 11. The Machines in Orbit. The 1989 and 2003 storms taught us about the grid. The last few years have taught us about orbit, and the lesson arrived in the form of a very modern kind of loss. In early February 2022, a company launched a batch of 49 new satellites into low orbit, part of the enormous constellations that now blanket the sky, to deliver internet from space. The timing was unlucky. A relatively modest geomagnetic storm, nothing remotely on the scale of Quebec or Halloween, happened to be underway. And here the quiet fourth wave of the convoy, the one we mentioned earlier, did its work. The storm had heated and puffed up the upper atmosphere, thickening the thin air at the altitude where the new satellites were temporarily parked. Thicker air meant more drag. The satellites, fighting to raise their orbits, could not climb through the increased resistance, and roughly 38 of the 49 were dragged back down to burn up in the atmosphere. A minor storm, the kind that barely troubles the grid, destroyed most of a launch. It was one of the clearest demonstrations ever recorded that the new economy in low orbit is exposed to space weather in a way the old satellites in high orbit never quite were. Then came May of 2024 and a storm that earned its own name. Space physicists call it the Gannon storm, after a scientist in the field who had recently passed, and it was the strongest geomagnetic storm to strike the Earth in about 2 decades, since the Halloween storms themselves. For a couple of nights the aurora spilled down across the middle of the United States and into parts of the world that almost never see it, and millions of people photographed a sky that their grandparents would have found alarming. Behind the beauty, the storm disrupted precision navigation systems badly enough that some farming equipment, which now relies on satellite positioning accurate to the inch to steer itself through fields during planting season, was knocked off its guidance and idled at one of the busiest times of the agricultural year. No grid collapsed, and that was partly luck and partly 2 decades of hard preparation. But the Gannon storm was a shot across the bow, a reminder delivered less than 2 years ago that the sun is fully capable, even now, of reaching down and touching the systems we lean on. Put those 2 recent events beside the older ones and a pattern emerges that is directly relevant to this morning. The threat is not shrinking as our technology advances. In some ways it is growing, because we keep hanging more of our civilization in places the sun can reach. More satellites in the drag zone, more of the economy depending on precise timing signals from space, more power flowing through grids that stretch across continents. The same storm that would have been a curiosity a century ago, when the most vulnerable technology was the telegraph, is now a threat to systems that touch nearly every part of daily life. And that is why people who study this have tried to put a number on the worst case. The numbers are sobering, and they deserve to be quoted carefully rather than dramatically. Serious studies of a truly extreme, once-in-many-decades storm, the kind that would rival the greatest event of the historical record, have estimated the potential economic cost to run somewhere between $600 billion and $2.6 trillion for a severe event striking a modern grid, with recovery measured not in days but in months to years, precisely because of those custom-built transformers that cannot be quickly replaced. That range is wide because the honest truth is that we have never taken a full Carrington-class blow with the grid we have now, so the estimate is a projection, not a measurement. But even the low end of that range, $600 billion, describes a blow to the modern world unlike almost anything short of a war. I want to be very clear about the distance between that worst case and where we actually stand this morning, because the gap is enormous and it matters. Nothing on the scale of Quebec or Halloween or even Gannon is forecast for today. There is no storm watch. The most likely path over the next few days remains an active region that fires some more flares and then rotates away without ever launching the great Earth-directed cloud that these historical events required. The trillion-dollar scenarios are the far tail of the distribution, not the centre of it. But the reason we walk through them is the reason forecasters exist at all. This is the one hazard where the warning comes in days and the damage comes in seconds, where the difference between a light show and a catastrophe is which way one violent region happened to be facing when it fired. And right now, that one violent region is facing us, which is exactly why the next strange twist in this story is so worth understanding, because at this very moment there is a wave of claims spreading online insisting that the timing of all of this is no accident at all, that the sky itself is lining up to pull the trigger. That claim deserves a real answer, and it is going to get one. Part 12. The cycle that's supposed to be winding down. There is a comforting story people tell themselves about the sun, and this week is a good time to take it apart, because the comfort is false and the region we're watching is proof. The sun runs on a rhythm of roughly 11 years. It builds from a quiet minimum, when its face is nearly blank, up to a raucous maximum, when spots and flares crowd the disk, and then it subsides back down toward quiet again. We are now past the maximum of the current cycle, and into the downslope, the stretch scientists call the declining phase. And the intuitive conclusion, the one almost everyone reaches without thinking, is that a sun on the downslope is a sun that is calming down, growing safer by the month, its worst days behind it. It is a reasonable guess. It is also, as a guide to actual danger, badly wrong. The reason it is wrong is that the number most people use to judge the sun's mood, the raw count of sunspots, is not the same as the sun's capacity for violence. The spot count does fall during the declining phase, but the individual regions that do appear can be every bit as complex, every bit as magnetically tangled, and every bit as capable of a great flare as anything from the peak. In some respects, the declining phase specializes in a particular kind of danger. It is the season when long-lived, well-organized structures can rotate around again and again, and when the sun's most violent single events have, historically, a nasty habit of occurring. We already met the clearest example a few minutes ago. The Halloween storms, some of the most powerful space weather of the entire space age, erupted from a sun that was well into its own declining phase, past its peak, supposedly winding down. Nobody who lived through those storms would describe a declining sun as a safe one, which brings us straight back to active region 4513. Here is a large beta-gamma-delta region, carrying the most dangerous magnetic configuration there is, firing a staircase of flares that has climbed to an M6.9, sitting in the sweet spot aimed at Earth, and it is doing all of this from a sun that a casual glance would call past its prime. That is not a contradiction. That is exactly what the declining phase looks like when it decides to remind you it is still armed. The falling spot count did not disarm this region. The sun does not need to be at its noisiest to produce its most dangerous single event. It only needs one region like this one, in the wrong place, at the wrong moment. And this week it has one. There is a second, smaller wrinkle worth adding, because it is part of the honest picture of the days ahead, and because it comes from a completely different feature of the sun than the one we have been discussing. Separately from the flaring region, forecasters have noted that a stream of fast solar wind is expected to reach the Earth later this week, flowing out of what is called a coronal hole. A coronal hole is not a flare and not an explosion. It is a gap in the Sun's outer atmosphere, a region where the magnetic field opens up instead of closing back down, and through that opening the solar wind escapes faster than usual, streaming out into space like water through a breach in a dam. When that fast stream sweeps past the Earth, it can stir the magnetic field on its own, lifting the disturbance level modestly, sometimes enough for a minor storm and a bit of aurora, entirely independent of anything the flaring region does. I raise it not to pile on the drama, but to be complete, because it means the coming days have two separate ways of becoming geomagnetically active. One is the dramatic, low-probability, high-consequence path, a large Earth-directed eruption from the loaded region in the sweet spot. The other is the mundane, higher-probability, low-consequence path, a gust of fast wind from a coronal hole giving the field a gentle shake. They are not the same thing, and it would be a mistake to confuse a minor ripple from the coronal hole with the arrival of something from the flaring region. But it does mean that if you see a modest disturbance register on the instruments in the next few days, it will not automatically be the big region firing. It might just be the wind. Keeping those two straight is exactly the kind of discipline that separates understanding this stuff from being frightened by it. There is one more thing worth knowing about coronal holes, because it changes how you should read the whole rest of this cycle. Unlike a flaring region, which flares unpredictably and then fades, a coronal hole is a long-lived stable feature that can survive for many rotations of the Sun. That means the same hole comes back around to face the Earth roughly every 27 days, the length of one solar rotation, delivering its fast stream on a schedule you can very nearly mark on a calendar. As a cycle winds down and the big flaring regions grow scarcer, these recurring holes become the dominant source of space weather, trading the drama of the sudden eruption for the metronome of the returning stream. When such a stream sweeps past, it does not slam into us the way a cloud does. It piles into the slower ordinary wind ahead of it, compressing it into a turbulent region that buffets the Earth's field for a day or two as it passes. It is the difference between being hit by a projectile and being pushed by a rising tide. The tide is gentler, but it comes back again and again on a rhythm the Sun keeps whether or not any region is flaring. So the declining phase is not a shield, and the quiet Sun is a myth this region is busy dismantling. That is the sober, physical picture of where we stand. But the physical picture is not the only story being told about this week, because out beyond the data, in the place where genuine events get wrapped in an invented meaning, a very different explanation for all of this is spreading fast, and it starts with a genuine coincidence in the sky. Part 13. The Coincidence in the Calendar. Here is where the story leaves the realm of the instruments for a moment, because something is happening in the sky over the next few days that has nothing to do with the Sun's magnetic field and everything to do with how frightened people are willing to become when unrelated events share a calendar. Two genuine astronomical events fall almost on top of this solar escalation. The first is that the planet Mercury reaches what astronomers call superior conjunction on the 27th of August, which simply means that Mercury passes around the far side of the Sun as seen from Earth, lined up behind it, hidden in its glare. It is a routine orbital event, one that happens on a regular schedule as Mercury lapses on its tighter, faster path around the Sun. You cannot even see it, because the whole point of superior conjunction is that the planet is behind the Sun and lost in its light. The second event is more spectacular. On the night of the 27th into the early hours of the 28th, the Earth's shadow falls across the Moon in a deep partial lunar eclipse, one so nearly total that the Moon slides most of the way into the dark central shadow, up to around 93% of its face swallowed, some accounts putting it as high as 96%, deep enough to blush the Moon a dull red and earn the popular name of a blood moon. It will be visible across much of the Americas and parts of Europe and Africa, and it is, by any measure, a genuinely dramatic sight. So within about a 48-hour window, three things happen. A violent Earth-facing sunspot fires and loads. Mercury slips behind the Sun, and the Moon turns red in the Earth's shadow. Three unrelated events sharing a stretch of the calendar, and that coincidence, that pure alignment of timing, has become the seed of a story spreading rapidly online right now. A story that says the skies are lining, that the planets and the shadow and the flaring Sun are connected, that the alignment itself is driving the solar violence or foretelling a much larger eruption to come. You will find versions of this claim everywhere at the moment, some framing it as ancient knowledge, some dressing it in the language of energy and resonance, some simply pointing at the shared dates and letting the implication do the work. The dates, after all, really do line up. The flare really did happen. The eclipse really is coming. When real events cluster like this, the temptation to draw a line connecting them is almost irresistible. I want to take that temptation seriously rather than mock it, because there is nothing foolish about noticing a pattern. Pattern recognition is one of the sharpest tools the human mind has, and for most of our history, treating coincidences in the sky as meaningful was a reasonable survival strategy. The night sky was a calendar and an oracle long before it was a physics problem. So when someone looks up and sees a red moon in the same week that the sun is throwing flares and feels, in their gut, that these things must be connected, they are doing something deeply human. The instinct is not the error. The error is stopping at the instinct instead of asking the next question, which is whether the connection your gut proposes can survive contact with what we actually know about how these things work. For nearly all of human history, this exact instinct was not a fringe belief, but the mainstream one. A blood-red moon and a darkened sky were read as omens across almost every culture that ever looked up. Warnings of war or plague or the anger of something vast, and a bright new light in the heavens, a comet or a nova, was taken as a message meant for the people below. Rulers kept astronomers on staff precisely to read those messages. So when a modern person feels a chill at the idea that a red moon and a raging sun in the same week must mean something, they are standing in a tradition older than writing. The difference now is not that we have become smarter than our ancestors. It is that we have learned, painstakingly and against our own instincts, that the sky is not a message and the coincidences in it are not authored. The red moon on the 27th is the ordinary geometry of the Earth's shadow, scheduled centuries in advance, indifferent to the sun's tantrums. Feeling the old pull toward meaning is human. Mistaking the pull for evidence is the error the last few centuries of astronomy were spent unlearning, and that is the honest tension of this part, so let me hold both sides of it plainly. The coincidence is real. The dates genuinely overlap. It is a striking week in the sky, and it would be dishonest to pretend otherwise, or to wave the whole thing away as if noticing it was stupid. But real coincidence and real causation are two entirely different things, and the entire discipline of understanding the sun rests on being able to tell them apart. The question is not whether Mercury and the Moon and the flaring region share a calendar. They plainly do. The question is whether Mercury sliding behind the sun or the Earth's shadow crossing the Moon can do anything at all to a violent knot of magnetism on the solar surface. Can the alignment in the sky reach out and pull the trigger on active region 4513? That is a real question with a real answer, and the answer is whether science has to do its work, gently but without flinching. Part 14. Why the sky can't pull the trigger. So let us ask the question directly and answer it directly. Can the position of Mercury, or the shadow of the Earth falling on the Moon, trigger a solar flare? The answer, as far as the physics can tell us, is no, and the reasons are worth walking through carefully, because they are more interesting than a simple dismissal. Start with the only force that a distant planet could plausibly exert on the Sun, which is gravity, and specifically the tidal part of gravity. The slight difference in pull across the width of an object that raises tides in our oceans. The Moon raises tides on the Earth because it is close, and the Earth is right there under it. Could Mercury or the Moon raise a tide on the Sun strong enough to squeeze a region into flaring? Run the numbers and the idea collapses immediately. Mercury is a small planet, and at superior conjunction it is on the far side of the Sun, tens of millions of miles from the flaring region we care about. The tidal force it exerts on the Sun's surface is almost unimaginably tiny, smaller by an enormous factor than the forces already at play inside a sunspot's own magnetic field. Asking Mercury's gravity to trigger this flare is like asking whether a feather laid on one end of a moving freight train could determine when the brakes engage. The scales are so far apart that the question answers itself. Now, look at what actually powers a flare, because this is the real reason the alignment is irrelevant. A solar flare is not driven by anything outside the Sun. It is driven by the magnetic field of the flaring region itself, that tangled, sheared, stressed structure we spent the early part of this video describing. The energy comes from inside that knot of magnetism, released when the field lines snap and reconnect into a lower energy arrangement. The trigger, the thing that decides the exact moment a flare erupts, is the local state of that field, how much stress it has accumulated, how close it has crept to the breaking point. It is an internal process, governed entirely by the physics of the region, playing out on the surface of a star 93 million miles away. A planet lining up behind the Sun tens of millions of miles beyond that changes nothing about the magnetic topology of active region 4513. The flare this morning would have happened whether or not Mercury was anywhere near conjunction, and the eclipse coming on the 27th will change nothing about what the region does next. I want to be fair to the more sophisticated version of this idea because there is one, and honesty requires meeting it rather than the easiest version. There is a small and contested body of research associated with a handful of scientists over the years that explores whether the combined tidal tugs of the planets might, over long timescales, nudge the overall rhythm of the solar cycle, the slow 11-year build and fade rather than any single flare. That work sits at the fringe of the field, it is genuinely disputed, and the mainstream of solar physics does not accept it as established. But even the people who pursue it are talking about the long, slow modulation of the cycle across years, not about whether a planet can set off a particular flare on a particular morning. Nobody serious, not even the boldest proponents of planetary influence, claims that Mercury's position this week reached out and lit off the M6.9. So the viral version of the claim is not a bold reading of a real theory. It is a leap past what even the fringe theory says into something the physics simply does not support. Here is the way to hold all of this at once, and it is the posture this channel tries to keep on everything. The solar threat this week is real. A violent region really is sitting in the sweet spot, really did fire, really does carry a 1 in 10 daily chance of an extreme flare aimed at us. That is worth your attention, and it comes from the data. The alignment in the sky is also real, a genuine and beautiful coincidence of a hidden planet and a reddened moon. But the line connecting the two, the story that the sky is orchestrating the sun, does not exist. You can look up at the blood moon on the 27th and find it stunning, and you can watch active region 4513 with genuine concern, and you do not have to, and should not, glue those two true things together with a false one. The sun is dangerous this week for reasons written in magnetism, not in astrology. And keeping those straight is not a small thing, because the same instinct that wants to blame the alignment for the flare is the instinct behind an even more persistent claim, one that says the sun is not just threatening our machines, but reaching down to move the very ground beneath our feet. Part 15. The other thing people blame on the sun. Every time the sun does something violent, a second claim surfaces alongside the alignment stories, and it is worth confronting directly because it is more plausible sounding, and therefore stickier. The claim is that solar flares trigger earthquakes, that when the sun lashes out, the ground answers. We actually walked through a specific version of this only a few days ago, and it is worth the callback because it shows how the claim works in practice. Earlier this week, when this same region was firing from the limb, a magnitude 6.7 earthquake struck near Peru, and within hours there were posts online tying the two together, presenting the quake as the terrestrial echo of the solar storm, a solar quake. The pattern is always the same. A flare happens. An earthquake happens somewhere on a planet that has dozens of magnitude 5 and 6 earthquakes every single week. The two get placed side by side, the shared timing is presented as evidence, and a causal story is born. It is the exact same machinery as the alignment claim, just pointed at the ground instead of the sky. So what does the science actually say? The honest answer has two parts, and I am going to give you both, because giving you only the convenient one would be its own kind of dishonesty. The bulk of the careful research finds no reliable connection. A well-known statistical study some years back, by researchers examining large catalogues of earthquakes against records of solar and geomagnetic activity, found no dependable correlation between the two, nothing that would let you predict a quake from a flare or a flare from a quake. That is the mainstream position, and it is held for a simple physical reason as well as a statistical one. The energy budget does not work. The energy a solar storm deposits into the Earth is real, but the amount of it that could plausibly reach the depth where earthquakes originate and act on a fault that is already loaded to near failure is vanishingly small compared to the colossal forces of the tectonic plates themselves. a fault that ruptures during a solar storm was, by every indication, going to rupture anyway. The sun did not push it. Now the second part, because there is one. In more recent years, a paper did report a possible weak statistical association between certain solar particle events and the timing of some large earthquakes, and proponents of the connection point to it as vindication. Honesty requires me to tell you it exists, but honesty also requires me to tell you where it sits, which is contested, not replicated to the standard that would settle the question, and far from enough to overturn the weight of evidence and the physical objection on the other side. A single suggestive study is how science raises a question, not how it answers one. The responsible position, the one the major geological agencies hold, is that there is no established mechanism by which a solar flare triggers an earthquake, and that the apparent links are best explained by coincidence and the sheer frequency of earthquakes on an active planet. When something rattles the ground within a day of a flare, that is not surprising. Something rattles the ground within a day of almost everything, because the ground is always rattling somewhere. The base rate is really the heart of why these pairings feel meaningful and are not. Our planet is seismically busy in a way most people never register, because the vast majority of its earthquakes are too small or too remote to make the news. Every single week, the Earth produces on the order of dozens of earthquakes of magnitude 5 and larger, scattered along the great fault systems that ring the Pacific and thread through the world's mountain belts. Magnitude 6 events happen many times a month, which means that on any given day the sun does something dramatic. There is a very high chance that a significant earthquake occurs somewhere within a day or two on either side of it, purely because significant earthquakes are always occurring somewhere. Line up two things that both happen constantly, and you will never run short of coincidences to point at. The Peru quake earlier this week was a real and serious event for the people who felt it, but placing it next to a solar flare and calling the pairing evidence is like noting that it rained on a day someone somewhere won a lottery, and concluding the rain picked the numbers. The coincidence is guaranteed by how often each thing happens, not by any thread running between them. I keep coming back to the same discipline because it is the thing that actually protects you from being misled. The Peru quake earlier this week was a real event, and the flare was a real event, and they were not connected, in the same way that this week's blood moon and this week's flare are real events that are not connected. The instinct to link them is human and understandable, but the region we are watching is dangerous for a specific bounded set of reasons, all of them about magnetism and radiation and induced electric currents in long conductors, and none of them about earthquakes. Loading the sun with powers it does not have, the power to shake the ground, the power to be commanded by a hidden planet, does not make it scarier. It makes it harder to see the real threat clearly, which is the last thing you want when a genuine one is sitting in the sweet spot. The real danger is quite enough on its own. It does not need embellishment, which leads straight into the most common accusation of all, the one that sits underneath every alignment story and every solar quake claim, the suspicion that the people whose job it is to watch the sun are not telling us the whole truth. That one deserves a straight answer too, and the answer might surprise you, because it cuts in a direction most conspiracy claims do not expect. Part 16. What the forecasters can and cannot see. The suspicion goes like this. If a violent region really is aimed at Earth, and a storm really could be coming, then surely the authorities know more than they are saying, and surely the calm official tone is a cover, a way of keeping people from panicking about something the insiders can already see coming. It is a natural suspicion, and this time the honest response is not defensive, because the reality is almost the opposite of a cover-up. Start with the thing people misread most often, the absence of a storm watch today. It is tempting to read that silence as concealment, as if the lack of an alarm means the alarm is being suppressed. But that is backwards. A geomagnetic storm watch is issued when forecasters have actually seen a fast, Earth-directed cloud erupt and can model it arriving. The reason there is no watch this morning is not that one is being hidden. It is that no confirmed Earth-directed cloud from this morning's flare has been identified with the confidence needed to post one. The silence is not a locked door. It is an honest statement that, as of right now, the thing that would justify an alarm has not been established. If that changes, if a clear halo cloud is seen barreling toward us, the watch goes up publicly within hours, exactly as it did before the recent storms we talked about. The system's default is to warn, not to hide, and here is the part that genuinely undercuts the cover-up story. Almost all of the data this entire video is built on is public, updated continuously, and free for anyone to read. The flare classifications, the region positions, the daily flare probabilities, the 3-day forecast, the state of the Earth's magnetic field, the alerts and watches and warnings, all of it is published in near real time by the official space weather forecasters and mirrored across a dozen independent trackers run by enthusiasts and researchers around the world. The 45% and 10% numbers I quoted you did not come from a leak. They came from a public bulletin. When I told you the region sat at 3 degrees north and 5 degrees east, I was reading coordinates anyone with an internet connection can read. This is one of the most transparent corners of science there is, precisely because space weather affects satellites and grids and airlines that all need the same warnings at the same time. There is no secret channel with better numbers. The forecasters are quite literally showing their work. What the forecasters cannot do is more interesting and more honest than any cover-up, and it is the real limit you should understand. They cannot tell you whether this region will fire an X-flare tomorrow, because the physics of exactly when a stressed magnetic field snaps is not predictable at that precision. They can give you a probability, a 1 in 10 day, but not a certainty because nobody can see inside the region and know how close its field has crept to the breaking point. And even when a cloud does erupt and head our way, the single, most important thing about it, the direction its embedded magnetic field is pointing when it arrives, often cannot be known until it's about an hour from Earth, when it finally sweeps past the spacecraft parked upstream of us that act as our early warning buoys. That last detail decides whether a cloud that hits us produces a spectacular but harmless light show or a serious storm, and we frequently do not get to know it until the cloud is almost here. The honest picture is not an authority that knows and conceals. It is an authority that shares everything it has and is candid about how much it still cannot see. It is worth knowing how that last hour warning actually works, because it is one of the quiet marvels of the whole system. Roughly 1 million miles from Earth in the direction of the Sun sit a handful of spacecraft parked at a special balance point in space, where they can hover on the sunward side of us, keeping watch. When a cloud of plasma comes barreling in, it sweeps over those spacecraft first, and in that moment they measure the one thing that matters most, and that nothing else can tell us in advance, the direction the cloud's own magnetic field is pointing. If it points the same way as Earth's field, the cloud largely slides past and the storm is mild. If it points the opposite way, the two fields link and the energy pours in and the storm is severe. But the cloud is moving so fast by the time it reaches those buoys that the warning they provide is measured in tens of minutes, sometimes less than an hour, before the same cloud reaches us. That is the actual early warning system for the most consequential part of a solar storm. Not days, not hours, often less than 1. It is enough time for grid operators to take defensive action and for satellite controllers to safe their spacecraft, and it is nowhere near enough time to be a secret. The moment those buoys see something serious, the alert is public almost instantly, because the whole point of them is to warn everyone who needs warning at once. That candor is the whole reason this channel treats the subject the way it does. We're not here to tell you a storm is coming, because as of this morning, the data does not say that. We are not here to tell you the alignment or the eclipse or a hidden planet is behind any of it, because the physics says they are not. We are here to tell you the truth, which is more unsettling than a cover-up and more interesting than a prophecy. A genuinely dangerous region is sitting in the most dangerous position on the Sun, aimed at us, with real odds of a real event, and the people whose job it is to watch it are watching it in the open, telling us plainly both what they see and what they cannot yet see. So the question is no longer what anyone is hiding. There is no one hiding anything. The question is simply what this region does next, from the seat it is in, over the next couple of days, while we watch alongside everyone else. And that raises the practical question you have probably been waiting to ask, which is what any of this actually means for you, tonight, wherever you happen to be watching from. Part 17, what this actually means for you. After all of that, the reasonable question is a personal one. If you're not an astronaut and you do not run a power grid, what does a violent region in the sweet spot actually mean for you standing in your kitchen tonight, 93 million miles from all this drama? The honest answer is a mix of almost nothing and something genuinely worth watching for, and it is worth separating the two. Start with the reassuring part because it is the larger part and you have earned it after all this tension. For the overwhelming majority of people, even a fairly strong solar storm is something you read about rather than something that happens to you. Your lights stay on, your phone works. The radio blackout this morning touched specialized users on specific bands for a few minutes and left the rest of daily life completely untouched. Even in the historic storms we discussed, the ones that damaged grids and satellites, most people's experience was either nothing at all or, at most, a beautiful sky. The systems that are vulnerable, the grids and the satellites and the polar flights, are watched and defended by people who have spent decades preparing for exactly this, and 2 decades of that preparation is part of why the recent strong storm passed with disruption rather than disaster. You're not standing on the front line of this. You are, for the most part, a spectator to it. Now, the part actually worth watching for because it is the flip side of the same coin, and it is a genuine gift. The very same energy that threatens transformers is the energy that lights up the aurora, and a violent region in the sweet spot, if it does fire a cloud our way, tends to push the northern and southern lights much farther from the poles than usual. That means that over the next few nights, if a storm does materialize, people well outside the usual aurora zones into the middle latitudes could get a chance to see the sky do something they may never have seen it do from their own backyard. If you have never watched the aurora, this is exactly the kind of setup, a loaded Earth-facing region during the darker end of the month, that occasionally delivers it to unexpected places. So the same event that has forecasters watching the grid could, for you, be an invitation to look up. There is a strange and honest beauty in that the thing capable of threatening our machines is also the thing that paints the most extraordinary skies most of us will ever see. If you do want to try to catch the aurora, a few simple things stack the odds in your favour, and none of them require equipment. Get away from city lights because the glow of a town will drown a faint aurora completely, and give your eyes a good 20 minutes in the dark to adjust. Look toward the pole, north if you're in the northern hemisphere, low along the horizon, because from the middle latitudes a distant aurora often shows up as a pale glow or faint pillars near the horizon rather than the overhead curtains you see in photographs from the far north. And here is the single most useful trick. Point your phone camera at that patch of sky and take a long exposure photo, a few seconds if your phone allows it. A camera gathers light over time in a way your eye cannot, and it will pull out reds and greens that are completely invisible to the naked eye, so a sky that looks merely a little odd to you can bloom into colour on the screen. Many people who think they have never seen an aurora have simply never photographed a sky that was quietly glowing above them. The best nights to try, if a storm does come, would be the darker hours well after sunset, and the forecasts that would tell you whether it is worth going outside are the same public space weather feeds we have been talking about all along. What should you actually do with all of this? Almost nothing, and that is the truth, not a brush-off. This is not a moment to stockpile or to panic, because the most likely outcome of the next few days, by the numbers, is that this region fires some more flares and then rotates away without ever launching the great storm that the worst-case scenarios require. The right posture is not fear, it is attention. Keep half an eye on the sky over the next few nights, both because there might be an aurora worth catching, and because the story of this region is genuinely unfinished. If you live somewhere the grid is fragile, the ordinary common sense of having a flashlight and a plan is never wasted, storm or no storm. But that is true every week of the year, and this week does not change it much. The single most useful thing you can carry out of this video is not a supply list. It is the ability to watch this unfold over the coming days and understand what you're actually seeing, to tell a real forecast from a viral rumour, a coronal hole ripple from a genuine strike, a beautiful coincidence from a cause. Because that is the thing this channel is actually for. Not to frighten you, and not to soothe you, but to hand you the frame that lets you look at a week like this one and see it clearly. A violent region, aimed at us, loaded, watched in the open. A sky full of real and unrelated wonders, and a stretch of a few days in which the sun gets to decide, entirely on its own terms and its own schedule, whether this becomes a story about a light show or a story about something more. You now know enough to watch that decision unfold with clear eyes. Which leaves only the last question, the one we started with, the one the quiet on the instruments this morning cannot answer. If a storm is coming, it is already on its way. And if it is already on its way, then the calm we are feeling right now is not what it seems. Part 18, the travel time of something already coming. Let me bring us back to where we began, to the strange quiet of this morning, because now you have everything you need to feel why it is so unsettling. At 10:02, the sun fired an M6.9 from a violent region sitting almost dead center on the disk, aimed at us. The light reached us in 8 minutes and blacked out the radio on the daylight side, and then it was gone. And ever since, the instruments here on Earth have read calm, no storm, no watch, a magnetic field as quiet as any ordinary day. We have spent this whole video learning why that calm is not the reassurance it appears to be. The light is the fast messenger, and it has already come and gone. If this morning's flare threw a cloud our way, that cloud is slow, and it is still out there, somewhere on the 93-million-mile road, and it will not announce itself until it is nearly here. So the quiet on the instruments is not proof that nothing is coming. It is at most proof that nothing has arrived yet. Those are very different statements, and the space between them is the space we are living in right now. Hold the whole shape of it in your mind one last time. A region that fired the biggest flare of the cycle 5 days ago while facing away from us. 5 days of patient rotation that brought it around to face home. A staircase of flares climbing through the night to this morning's near-X event. A 1 in 10 daily chance of the top class from the most dangerous seat on the sun for another couple of days. And an Earth that, for the moment, feels absolutely nothing. Every piece of that is real, and every piece of it came from the data, not from the sky's coincidences and not from anyone's fear. The danger this week was never that the sun grew more violent. It was that the violence turned to face us, and that the turning is not yet finished. There are a few specific things the people who watch this will be looking for over the coming days, and now you can watch for them too. They will be looking to see whether this region actually produces an X-flare while it lingers in the sweet spot, because that is the single event that would turn this from a watch into something more. They will be looking to see whether the cloud hinted at by this morning's radio signature is confirmed to be aimed at us, and whether in the next day or so a storm watch finally goes up for the window around the 27th and 28th, the same nights the moon turns red, which would be a genuine collision of the real threat and the harmless coincidence in the same sky. And they will be watching to see whether that fast stream of solar wind arrives from the coronal hole later in the week and stirs the field on its own, a smaller and separate ripple not to be confused with the big region firing. Those are the threads, and they are all still open. But the one that matters most, the one this entire video has been circling, is the simplest and the least answerable. For the next couple of days, the most dangerous region on the sun is aimed directly at us, loaded and firing. The blackout has already happened, the instruments still read calm, and the only question that actually matters is whether that calm is what safety feels like, or whether it is simply the travel time of something that has already left the sun and is on its way, silent, invisible, and slow, across the dark. Watch the sky over the next few nights. Not out of fear, but because for once you will know exactly what you're looking at. And if the north begins to glow in a place it never glows, you will understand, before anyone has to tell you, what it means that the quiet finally broke.